So we're going to discuss a couple components of functions that are graphed, and I think we're going to specifically look at mostly polynomials, but not just polynomials. We're going to talk about what are called extrema, sounds exciting, and average rates of change. We've already discussed rates of change for quadratic functions back in Algebra 2, but also in this class. We're going to continue on with that topic now that we're going to have more exciting polynomials to look at. So we're going to be looking at when your function is increasing versus decreasing. When is it constant? Where does it change from increasing to decreasing? We're going to come up with some ideas that are called critical points, relative minimums versus an absolute minimum, relative maximum versus an absolute maximum, and then those terms are referred to as the extrema. I think this is the lesson where we also talk about concavity. That sounds frightening, right? So concavity is it's actually a calculus concept, but it's easy to visualize on our graphs. And we're going to break it down for you so it's nice and easy. If you are coming from a regular Algebra 2 course instead of an honors Algebra 2 course, this is probably going to be a moment where you need to really stop and maybe get some help on, in particular, the increasing and decreasing behavior and also the concavity. It's very likely that your Algebra 2 teacher never talked about when the function was increasing and decreasing. It's not incredibly difficult. It's still going to be an interval notation concept. It's just a lot to think about. This is a really huge lesson. So I expect to see lots of hits on this lesson, okay? Let's talk about what it looks like when you're increasing versus decreasing. So the first thing you have to get around is that we always read interval from least to greatest left to right for domain intervals. When I ask you for an interval for which the function is increasing, I'm referring to a domain interval for when your function is going uphill when read from left to right. So this picture illustrates what increasing looks like. And the first thing, we used to teach this in Algebra 2. We kind of ran out of time some years, so we skipped over this concept. But in honors Algebra 2, I think you guys did see this. The arrow really confuses kids because they're like, oh, but it's going down. That's not how we read an interval. It goes from left to right. So if I was on a roller coaster and I was watching this, this is you at the first part of the roller coaster, you are increasing, 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 increasing all the way up to the top. Now, when you don't increase nor decrease, you are considered to be constant in that part of the function, so constantly. And then here's going downhill on the roller coaster, decreasing, decreasing, decreasing. So you have to get over the fact that there's arrows. You almost have to ignore the arrows completely, which I know is irritating, but while you're thinking about when is it increasing, when is it decreasing, pretend there's no arrow, because I think it'll relieve some stress. So it's increasing or rising from left to right. From the domain interval, remember these are all domain intervals, of negative infinity up until 5, because at this point right here, the roller coaster stops increasing, and now it's that boring part where it doesn't go anywhere. Constant or flat from negative 5 to 0, and then it switches again. And now it's going to be decreasing roller coaster. Wrong way. Decreasing roller coaster from 0, and then it keeps decreasing forever. It's like the worst roller coaster ever. All right. These points right here, they're important. And we're going to talk about, why they're important. When you go on to calculus, you're going to find ways to actually find those points. Here, we're just going to kind of interpret them visually from the graph. So increasing on an interval for which any 2 points results in a positive change. So this is a very weird way of saying like it's going up. So if you start here and then you figure out this point right here and you figure out the y values, like this y value, let's say it's like 3, and then this y value, let's say it's like 3.5. That went up, so it's increasing. It's a really stupid way to say it, right? Decreasing would be the opposite. So like here on this first value, maybe this was the y value of 4, and then down here his y value is like 2.5, so it's decreasing. And then constant means there's no change in the y value. So sometimes I feel like math textbooks do a really good job of making it so convoluted that it seems horribly difficult, but what they're doing is they're taking the universal language of algebra and symbols. So that way, like I could have a kid, and we do have this sometimes. We have kids come from other countries. They just were, stuck in our classroom in the middle, and they hardly speak any English. And I can tell you now, I don't remember anything from my other languages, but we all kind of speak math. So that's nice, right? Intervals, be careful. a function is neither increasing nor decreasing at that particular point. So we're going to be using parentheses when we do interval notation for these. There are some teachers out there who use brackets. You should not, because at those points, they're neither increasing nor decreasing. So technically, you should always use parentheses. All right, so here, we're going to be estimating from the graph on this first practice problem. I don't want you to use your calculator to get the exact values at the moment. If you don't mind, then I don't mind either. All right, so let's talk about what's some vocab. A relative max versus an absolute max. A relative max is any time where you have a bump up like this. So any sort of, so it goes from increasing to decreasing. An extrema, that's one of the types of extrema. It doesn't necessarily mean it's the highest point in the graph. If it is the highest point in the graph, that's what we call an absolute maximum. You're going to notice on this graph, there are no absolute maxes or mins because of these stinking arrows, right? It's never going to stop. There's no top or bottom point where I can say, yep, that's absolutely the smallest y value you will get. It's not going to happen. So I jumped the gun and I wrote none there, but that's okay. Let's talk about where this relative max is located. So this right here is a relative max, and then this is another bump up relative max. So I just want to know, well, I guess I kind of want to know. Oh, there are two lines. Good news. There's two relative maxes. I was worried because there wasn't two lines, but it's down here. So there's a relative max. The first one, let's say it's at the ordered pair negative 1.5 comma 0 roughly, according to my eyes, but I'm old, so maybe it's wrong. So make sure you put them in the right spot. The maximum value there is actually the 0, and it occurs at x equals negative 1.5. Let's go ahead and keep on the maximum train of thought. This ordered pair here is like 0.5 comma, I don't know, negative 1.2. I'm just not like making it up, so I don't really know. I don't know, maybe that's totally wrong. I have no idea. All right, so max of, what did I say, negative 1.2. Again, I got old eyes, guys, so I might be way wrong at 0.5. Now let's talk about the minimums. Here a dip down, that would be a minimum. That's a minimum. These are relative minimums. They are not absolute. This ordered pair is at like negative 0.5, comma, negative, I don't know, 1.7. Again, you could argue with me over that one. This guy is an ordered pair of roughly, let's see, 2.5, let's go with. And negative, I can't read my own writing. Oh, that's confusing. That's going by twos. Oh, I didn't notice I was going by twos. Let's go back and fix this. This is negative 2.2. All right, so that would be negative 4, let's say, right there. Oops, wrong color. Okay, so looks like I need to go back and fix this one. Relative max. I hate when they do that. I feel like if you're going to measure one of the axes by twos, then do the other one as well. Anyways, relative minimum, there's two of them. So this first one I found was a value of negative 1.7 at x equals negative 0.5. And then the next one I found was a minimum of negative 4 at x equals 2.5. Again, you can argue with me. I thought it was 2.3 or whatever. I don't care. If we use our calculator, we'll get absolute values. Sorry, I had to pause the video. Got a phone call. All right. So, increasing and decreasing behavior. This is about to get real messy. So the first thing I'm going to do is, well, hi, baby. I was going to erase all my marks here, but I kind of feel like I need to leave them. Because when I ask you for when the function is increasing, that's when the roller coaster is going uphill. So like here, it's increasing. But then at this extrema, it switches to decreasing. And then it's increasing again from here to here, and then switching back to decreasing, and then increasing again. So what we have to do is translate that to domain intervals. Ready for this next? No, we gotta eat dinner in a minute. Let's hurry up and finish this lesson. Okay. So it is increasing on the domain interval. It actually starts off as an increasing function. So negative infinity to this guy right here, which remember I'm looking at domains. I'm looking at x's. So negative 1.5. And then it's also increasing, so union, or here to here, so negative 0.5 to 0.5. So those extrema, those max and min points, super important for this part. And then it increases again from 2.5, and then it keeps on increasing. A roller coaster of death, apparently. To infinity. All right, so that's increasing intervals. Oops, I guess I was supposed to write that right there. My bad. And then decreasing interval. So the decreasing interval, I'm going to write over my screen if I go there. I'm going to go here. Decreasing interval is from here to here, and then here to here. So pretty much everywhere else. So from negative 1.5 to negative 0.5 and 0.5 to 2.5. What do you think this looks like, Nats? That's my decreasing interval. All right. You can technically leave off the union symbols for those intervals. I think according to our book, but I really like the union symbols. So think about that. Make your teacher happy. All right. So remember, end behavior. I like to say function first. So the function approaches something as x goes to the left, and the function approaches something else as x goes to the right. So I forgot what this looked like. So if I go back to my picture, on the left side, over here, a function's going down.
Down.
Do you know how to say down really fancy yet?
No.
No. Negative infinity. And then over here on the right, function's going up. Any idea how to say up really fancy yet?
Well.
No. Positive infinity. And again, remember your end behavior interval can be backwards. You can say x first versus f of x. I don't care as long as you're consistent. Yes, sir. Oh. Okay. You want to confirm this behavior. Oh, calculus is needed to confirm the behavior. All right. Well, we don't know calculus, so good news. This is pre-calculus. We're going to be using a lot of graphing calculus. Okay, critical point. Critical point is where your function switches its concavity, or it's where it switches its increasing to decreasing. So critical points are any maximum or minimum extrema are critical points. But we also have to talk about something called an inflection point. That's a pre-calculus book. So an inflection point is when your function changes its concavity. Let's talk about concavity. You have two options. You have concave up, and then you have concave down. So what does concave up look like? It looks like this or this versus concave down, this or that. Does this look like a smiley face at all to you, Natalie? Like a mouth of a smiley face? Maybe. So,
Banana cut in half. Take a banana just cut in half.
all right, she's got a point. The concave up is referred to, like if you want to think of it in non-mathy terms, it's a smiley face that's happy. So a concave up portion of the graph would be happy face.
No, that's a smile.
And concave down would be sad face.
That's a face. That's a sad face. That's a weird banana upside down. That's a smile.
Always a critic. All right, so the inflection point is the point in which it switches from happy face to sad face or vice versa. So let's write a little, oh, I was supposed to write this down here. Concave up, concave down, over there. Inflection point is, it's an estimation. Between your max and your min, your extrema. So these polynomial graphs are typically super symmetrical. So if you have a maximum of a graph like up here, minimum down here, the halfway point between those two is going to be where we're going to estimate our inflection to, where it changes from a sad face to happy face.
Honey, is that like a small spotboard?
Yeah.
Is it?
Technological abilities. It should be. I mean, I can't really draw, but it's all right. Let's see this in action. This screen here is from your textbook. It has a very mathy explanation of all of these concepts. A relative max versus relative min. It also talks about absolute at some point on the screen, I believe. Please don't touch. It gives you some nice visuals if you want a graph that actually looks good versus what I graph. And like I said, the concept of maximum versus minimum, like these are words we've heard before. So if you've grown up speaking the English language, like this is not a big confusing thing. This is a big confusing thing from your book. So I almost would rather not look at it if you don't mind. Again, calculus is needed to confirm. That's why we use the calculator in PreCalc because we don't know calculus. So this next example, this is on the back now, I think. This is where we're going to do the whole shebang. We're going to use our calculator. We're going to sketch it. It's going to be real ugly because I'm sketching it. You're going to state the x values for which all these extremas occur, or actually the points in general. And we're going to use all those extremas and those critical points to figure out increasing and decreasing intervals, concavity, and also the inflection point itself. So I almost feel like that's in a backwards order. I think you want to find, yes, the extrema first, then we'll talk about increasing and decreasing. And then I think we should find the inflection points because you're going to use those to figure out the concavity interval. So yeah, I digress. Yeah, go watch some TV. Probably some YouTube. All right, so if I graph this on the calculator, which, you know, go ahead and pause the video and get this typed in. I'm not going to because I kind of know what this looks like already. And since I can't graph to save my life, it's going to look really ugly. So, you know, whatever. It looks something like this. That's not good. It's supposed to be symmetrical. Didn't turn out. All right. Anywho, let's talk about everything we're going to figure out. So I noticed on this graph there is a relative max right here. And then there is a relative min. There's two of them. Actually, you know what? Take that back. That is an absolute minimum. Turns out that they're going to be the same y value. It is possible to have like one relative and one absolute, so just keep that in mind. We're going to figure out where this function is increasing, where it's decreasing. I would like you to find the inflection points, I should say, and then concave up and concave down. All right, ready for this? Whew. One thing at a time. So on my calculator, I'm going to have to figure out the location of this ordered pair using the maximum finder in my calc menu. So you're going to go to second trace and then choose the maximum finder because that's a maximum. And you're going to do left bound, right bound, enter. And no surprise here, it's going to come out to the ordered pair 0, 0. This guy is the ordered pair 0, 0, but I'm just writing down 0 because remember I'm going to give a domain interval, so I only want the x value is the only part I'm interested in. So this minimum here, which again, I'm going to go to the second trace, and this time I'm going to choose minimum. This ordered pair comes out to negative 0.97, negative 5.03. So all I'm going to really be interested in, though, is that negative 0.97 part. Spoiler alert, there's some symmetry. So this guy over here is positive 0.97, negative 5.03. But notice both y values were the same. So that's why we considered it an absolute minimum. They were the same y values. Doesn't dip down forever. It's an even function. That's what's happening here. All right, so increasing versus decreasing. Starting at the left of the curve, this is, remember, think about a roller coaster. This is going downhill until here. And then it's going uphill. And it's going downhill again. It's going uphill again. So it's increasing from negative infinity until negative 0.97. And then it increases again. No, it decreases. I did the wrong one. All right. That's why we use erasers. Okay, decreasing from negative infinity to negative 0.97. And then also from 0 to positive 0.97. And that was it for decreasing. Now back to increasing. My bad. Negative 0.97 to 0. And positive 0.97 to infinity. Notice the increasing and decreasing for this curve basically took up the whole thing because there was no point in the curve besides the critical points, the extrema, where it was constant. So also notice the use of parentheses instead of brackets. Let's talk about inflection points. So the inflection points would happen halfway between, and this is going to be really hard to see, so I'm going to have to use another color here. I'm going to erase the screen. The inflection point would happen halfway between this minimum and this maximum, and also between this maximum and this minimum. So if you kind of notice right here, I'm just estimating, oh gosh, I need like another color. Right here, we got like a frowny face, a sad face. But here is a happy face, and here's the other part of the happy face, right? So the inflection point is this dude and this dude. So I need to figure out where that inflection point is. Well, it's halfway between those two x values. So if I do a little side algebra, it's not even algebra, it's arithmetic. Halfway between, remember this was negative 0.97 and this is 0. So if I find the halfway point, negative 0.97 plus 0 divided by 2, you know, it's not super exact, but it's negative 0.5. And then if I want the y value for that inflection point, I could, you know, plug that into the function. I think it came out to negative 2.09, excuse me. And then there's another inflection point at, you guessed it, positive 0.5. They're not always this symmetrical. Well, they're always symmetrical, but it's not always this pretty. Still at negative 2.09. So when is the concave up? Remember, concave up is happy face. So it is a happy face right here and then right here. So that would be negative infinity until this first inflection point, which is negative 0.5. And so you can put a union, or you can just write the word and in this case. Positive 0.5 to infinity. Now don't confuse inflection point. These are ordered pairs. Everything else has been an interval for like increasing, decreasing, and concave up and down. It is confusing. It's just, you know, in math, we just have to appreciate the context of the question and understand what we're asked. That's why it's confusing for kids, I know. All right, concave down. There's only one part of this graph where it was a frowny face. Remember frowny face, concave down? And that was the green part that I highlighted. So that was from negative 0.5, positive 0.5. You know what I need? I need that graph graphed like 5 times, and then I could have scribbled all over that graph, like in all different colors, right? That was really, really tough. That was a lot of stuff to think about. Let's do one more of those. Let's see if I can do a better job of graphing. You know that's not going to happen, right? All right, so here. When I graphed this in my calculator, it looked something like this. I don't know how great I just did. Probably not great. What a surprise. I can see a max and a min. Unfortunately, they're relative. They're not absolute. All right, it doesn't really matter, but they're turning points. That's the important part. So we have a max, which I'm going to find on my calculator, and a min. I'm going to figure out when this guy was increasing versus decreasing. Good news is, because it's a lower degree function, it's only a 3rd degree, it's going to be less work, so we got that going for us. Inflection points is what I wanted to do next. And then we're going to do concave up and also concave down. All right, starting with maximum. So pause the video, get the function typed into your calculator, and we're going to have to figure out both of these extrema. So this maximum, I believe, is at negative 108. So you had to really mess with your window. Wow, 108. Hopefully you had a little perseverance in getting your window right. And then this minimum here, I didn't do a good job of graphing it. What's new? This is at the ordered pair 0, 0. Again, finding these extrema algebraically for polynomials that are a higher degree that aren't quadratic, you're going to have to use calculus. Unless you can hurry up and figure out calculus, you're going to have to use your calculator. Remember, there's a lot of emulators online. Your phone apps work great for these. Ideally, if you're in PreCalc, that probably means you're going far in life in math, so just go ahead and get your own calculator. ask her for your birthday or something. Increasing. If I look at this picture, remember, ignore the arrows, just look for going up the roller coaster. So we are increasing here, then we're decreasing here, and then we're increasing again here. So the x values are what I'm going to refer to for the domain. So it is increasing, I'm going to do it right this time, from negative infinity to negative 6, and then it doesn't increase again until you hit 0, and then goes forever. So it's decreasing from negative 6 to 0, which would be the other part of the interval, or the function's interval, domain interval. The inflection point, I have not calculated them yet because they're in the middle of my extrema. So there's only 2 extrema, which means I only have to find 1 inflection point. So in between negative 6 and 0, I got this. Negative 6 plus 0 divided by 2 is negative 3. So the inflection point is at negative 3, comma, plug in negative 3. I already did this, so why am I doing it again? It is 54. And then, if you notice, concave up would be a happy face. So this is not a happy face, but from here to here is. So this is my concave up part right here. So that is from, what did we just find? Negative 3, right? So negative 3 to infinity. And then it's concave down from here to here. That's a sad face. Any part of the sad face. So that would be from negative infinity to negative 3. Whew. Well, good news. That was easier. It was less steps. So when I send you homework or a test, just be like, please be a lower degree polynomial. That would be awesome. All right. So for this next one, they wanted you to just estimate from the graph. If you want some more practice, go ahead and pause the video and give it a try. You don't have to actually find the max, min, yada, yada. I think for the sake of time in the lesson in class, probably skipped this because this is a really long lesson. All right, application. We love these. So we got that box again that doesn't have a top. It has a square base. And we're going to be making a piece of cardboard, cutting equal size squares from each side of the corners. So this time, yes, you have to suffer through one of my pictures. Sorry. Got a square. The sides are 18. Okay. That is done that way. Totally nailed that picture. And we're going to cut off corners. They're going to be the same size though, right? So they're all X. We're going to write a function for volume of this box. So if I think about the volume of a box, it is length times width times height. So for this particular box, each of the length and width are going to be the same. It's going to be 18 minus 2x because, once you cut off those corners, that's what you have. So 18 minus 2x, and then another 18 minus 2x. And then the height of the box is however big those cuts were, so x. I know I wrote that in a weird order, but get over it. All right. I am not going to find this in any sort of algebraic method. I'm going to graph this on my calculator. So I'm going to go to y1, and I'm going to get this baby typed in. You don't even have to simplify it. So go ahead and pause the video, get it typed in. You're going to have to mess with your window, though. So I would think for like x's, because they're representing how much we're cutting off the box, like you're obviously not going to go less than 0 because that would not make a box. And then if you cut off too much, you'd have no box. So like 9 would leave you with nothing if you cut off 9 from both ends. So 0 to 9 is a good X window. The volume of the box, however, it's going to be kind of big. So you can try zoom fit, see if it matches magically. Usually I have a lot of luck with zoom fit. But the idea is you're looking for a maximum. So if you don't see a maximum extrema, keep going up in the window. You got to go pretty far up. Turns out that the max is located at the point 3, comma, 432. I hope I didn't just spoil that for any. So what that means for us is that 3 inches is inches, right? Is how big we're going to make the cut. And the 432 is the volume that we're going to come up with. So that is the maximum volume if you happen to cut off 3 inches from each corner. So what value of x maximizes volume? That would be 3 inches. And then max volume is 432 inches cubed. Labels are good. What's the relative minimum of the function? So depending on your window, you might have not seen this. If you use my window, I think you will. The minimum, It like drops down right here at the 0.90. So what does that mean for our problem? Well, think about that. If you cut off 9 inches, you're going to have no box because you just like cut your paper in half or cardboard in half. So the relative minimum basically is like the end point of the problem. If you go beyond that extrema, you're talking like negative volume or no, you're not talking about anything. You don't have any material left. So if I was trying to come up with an appropriate window, that extrema would be a good stopping point. Some would argue, even going that far is too big. Obviously, you're not going to go down to a volume of 0, but that's what that means. All right. So average rate of change. We've seen this before. It's called the secant line. It's a connection of two ordered pairs, and the closer the points are together, the more accurate the average rate of change becomes at that particular value. This is a calculus concept again, but essentially, when we first start off with average rate of change, we relate it to slope, which is the definition of slope, average rate of change. So for slope, it's always between 2 points. When we do average rate of change on curves, because there's so many points on a curve, you can keep bringing them together, and then you'll get a more accurate description. But we've already done this, guys. It's like easy lemon squeeze. Let's do this. So I want the average rate of change on this interval. So these are 2 x values that I'm going to be using, which means I like to write them as ordered pairs. -3 comma something and -2 comma something. Now, the something is what you have to figure out. So if you plug in -3 for all your x's into this function, I already did this, so I'm going to cheat and get it. You get 29. And then same thing this time, I want you to plug in -2 for all your x's into that function, and I'm going to cheat. I already did it. I got a 1. And now we calculate rate of change, which is fancy talk for slope. You know what you can call it M? Let's call it average rate of change. Fancy, right? All right, so 1 minus 29, y2 minus y1 over x minus x1. Don't pull a dyslexic move like I'm about to do. All right, -28 over 1. So my average rate of change is -28. Like, it's really stinking easy, right? The same thing here. My first ordered pair is going to have an x value of 1, and then the next ordered pair, x value of 3. So going into the function, I already did this, so I'm going to kind of pull the numbers. I know you guys can plug in just fine. Just watch your parentheses. Some of you are like big believers in the table. You like to use the table for this part. That's fine. 47 minus -5 over 3 minus 1. So 52 out of 2 over 2, excuse me. So the average rate of change in this question is 26. I'm not worried about you on that stuff. We've done average rate of change a lot. In a previous lesson, we talked about what happens as you become closer and closer and closer together. And we saw what happened, and it was good stuff. All right, good luck.